at 20 Celsius, the vapor pressure of pure cyclohexane, C6H12, is 77.5 millimeters of mercury, while the vapor pressure of pure hexane, C6H14, is 124 millimeters of mercury. Given a solution containing 40 grams of each, compute the solution vapor pressure. You should be able to recognize this as a Raoult's law problem. In other words, if we drew a diagram, we would have a liquid phase and a vapor phase. And we'll let C be cyclohexane and H be hexane. So we have cyclohexane and hexane in the liquid phase. It doesn't say both are volatile, but because I've given you a vapor pressure of both the cyclohexane and the hexane, that means that both are volatile. Both can evaporate into the gas phase. So you're going to see some cyclohexane and some hexane in the gas phase. And the total vapor pressure above that solution is going to be the sums of the partial pressures of the cyclohexane and of the hexane. So this is a Raoult's law problem. We want to compute that total pressure. So let P be the variable for pressure and T for total. That's our symbol for total pressure that we're going to compute. And that's going to be equal to the sums of the partial pressure of the cyclohexane and the hexane. Now that's not the Raoult's law equation I gave you before, but it's a different version of the Raoult's law. The Raoult's law version of the equation is, we'll say that total pressure is equal to the mole fraction of the cyclohexane times the vapor pressure of pure cyclohexane plus the mole fraction of the second component hexane times the vapor pressure of pure hexane. That superscript 0 means pure. So to compute this total pressure, we need 4 numbers in this equation. So let's see if we can pick them out from what we're given here. It says that the vapor pressure of pure cyclohexane is 77.5 millimeters of mercury. So we could say that let P be the vapor pressure of pure cyclohexane, and that's 77.5. Tack on a unit, millimeters of mercury. That's how we translated that phrase into a variable symbol and then assigned a value to that symbol and then tacked on a unit. So what else we're given here is the vapor pressure of pure hexane. So we'll construct a variable symbol for that. P for pressure, H for hexane, and for pure hexane, we put that superscript 0. We assign a value of 124.0 and use its unit, millimeters of mercury. So we have this number here, which is 77.5, and we have this number here, 124. So to finish off, we need these 2 mole fractions. All right, so read on through the problem. It says that we're given 40 grams of each. Well, these are mole fractions here. They don't match up with mass, so you could not put in a 40 for the XC and the X sub H. So we're given mass. We'll let lowercase m be our symbol for mass. Mass of hexane is going to be 40.0 grams. That's going to be equal to the mass of the cyclohexane as well. We're going to have to translate somehow these masses to mole fractions. So, how can we do that? Well, we could actually rewrite these equations. Now, you don't need to go through this much detail. Using the definitions of moles here for mole fraction. So, the mole fraction of cyclohexane would be the number of moles of cyclohexane, where N is our symbol for moles, over the total number of moles, cyclohexane plus hexane, times that pressure of cyclohexane, pure cyclohexane, 77.5. And then the second term would be number of moles of hexane over total number of moles times that number there. We're still not there though, because again, we're given mass, we're not given moles. So what we're going to do is we're going to take mass, M, convert to number of moles, N, plug them into this equation, and then convert that to mole fractions. Well, to change mass to moles, you can memorize an algorithm. Number of moles is equal to mass over molar mass. Or you can use dimensional analysis. This is mass in grams over molar mass in grams per mole. The grams cancel, you get moles in your answer here. We're going to need the molar masses of both the cyclohexane and the hexane. If you're wondering about the chemical structures of these compounds here, the cyclohexane consists of 6 carbon atoms in a ring. Approved chemical symbolism for this structure here. Each vertex here in this polygon, in this hexagon, represents a carbon atom. And the hexane itself is a straight chain compound. 1, 2, 3, 4, 5, 6. You could do the zigzag terminology in chemistry. Each vertex here, 1, 2, 3, 4, 5, 6, represents a carbon atom, and each carbon atom has 4 bonds, C6H12. You could do this instead, and tack on each of these being hydrogens. In this cyclohexane structure, there's actually 2 hydrogens on each carbon in that apex there to get 12. How this solution forms is that these are both hydrocarbons. They contain only carbon and hydrogen. And if you remember back to 121, carbon has an electronegativity of 2.5 and hydrogen 2.1. The difference in electronegativity between a C and an H in that CH bond is 0.4. That's less than 0.5, making these carbon H bonds nonpolar. So every bond in these molecules is a nonpolar covalent bond. That's going to make the overall compounds nonpolar molecules. Since they're both nonpolar, they can mix together through London dispersion forces. So the London dispersion forces between the cyclohexane and the hexane are going to help them mix together. Anyway, we need to convert these masses to moles. So we need the molar mass of the cyclohexane. Molar mass of cyclohexane, that's going to be equal to 6 carbons times the atomic weight of carbon plus 12 hydrogens times the atomic weight of hydrogen. 84.18. And then for the hexane, that molar mass is going to be equal to, again, 6 carbons and 14 hydrogens. So I could actually crank it out, or I could realize that it's going to be the mass of the cyclohexane plus 2 more hydrogens, 2.02 added to the 84.18, 86.20. So they're almost the same. I mean, so an approximation for the mole fractions would be that they're similar to each other. We have those molar masses. Next, we're going to convert the mass to moles. So for the first one here, remember we're letting N be our symbol for moles, and then the subscript, say for cyclohexane, would be a C. You can calculate the number of moles in 2 ways, using the algorithm mass, 40.0 grams of cyclohexane, divided by the molar mass of cyclohexane, which is 84.18 grams per mole. mass over molar mass. Or dimensional analysis, 40.0 grams. You put that over 1 times 1 mole. So 40 divided by 84.18 is 0.475. Likewise, we can compute the number of moles of hexane. The algorithm, divide the mass by the molar mass. Or dimensional analysis. Right, so then we can plug these into this formula here. We could compute the XC, the mole fraction of the cyclohexane. That's going to be the number of moles of cyclohexane, 0.475 over the total number of moles. Save some room there. We could do the same thing for the mole fraction of hexane, but it's a lot easier to get that last mole fraction by subtraction. Remember, mole fractions always add up to 1. So if you only have a binary solution, you can get the second one by subtraction. It's going to be a lot easier than plugging the numbers into this equation here and cranking it out. So we're going to say the mole fraction of that hexane is 1 minus So then we can plug that in, and we get for x sub c times 77.5, and for xh so this first number here would represent the partial pressure of the cyclohexane. It's how much pressure the cyclohexane is exerting in that space above the liquid. And this second number here would be the partial pressure of the hexane. We can sum up pressures to get the total pressure. It's our total pressure. So I'd probably round it off to this. You conserve a number of decimal places. So each of these should have 1 sig fig. We wouldn't keep that in our final answer. We'd probably change that to a 3. All right. It round up to this. On a test, I will count some problems for significant figures, usually 1 point, and others I won't care about it. All right, so we've reviewed Raoult's law. Let's go back and do freezing point depression and boiling point elevation. So let's review what boiling point is. We're going to take water as an example. So we have a beaker with some liquid water in it. There's our separation between the liquid and the gas phase. And we heat up the liquid very gradually. The air bubbles escape. Then as we heat it up, the liquid expands a little bit in the volume. Finally, when we get to close to 100 degrees Celsius, we're going to see steam bubbles form in the liquid. So these aren't representing molecules here. These are representing steam bubbles, water in the gas phase. And because the steam is a lot less dense than the liquid is, those bubbles rise to the surface, break out, and they exert an upward vapor pressure. When the upward vapor pressure coming out of the liquid is the same as the atmospheric pressure, boiling happens. You have an equilibrium. If you put this in a closed system here, you'll have an equilibrium between the rate of evaporation and the rate of condensation. If you're not in a closed system, then the water is just going to boil away or evaporate away. But boiling occurs when the vapor pressure of the liquid coming out is equal to the vapor pressure of the air. We're close to sea level, so we're close to 1 atmospheric pressure. So to have boiling occur here, it's going to happen at 100 degrees Celsius when 1 atmosphere of vapor pressure comes out, which would be 760 millimeters of mercury. And this is the chemical equation that explains what happens. Water in the liquid phase at 100 goes to water in the gas phase at 100. When you're in a closed system, you actually have an equilibrium. So we're not trying to emphasize that here. If we go out to Denver, Colorado, which is, I guess, a mile high, right? Water boils at 95 degrees Celsius because when you go up in altitude, there's less air molecules, it becomes less dense, and the pressure is less. So because the atmospheric pressure a mile up is 0.82, okay, this would be like 0.82 atmospheres exerting down on the liquid. You only need 0.82 atmospheres of vapor coming out to have boiling occur, and that occurs at 95 degrees Celsius. So boiling point changes with atmospheric pressure. Another thing about boiling is that for different types of substances, some have strong IMFs and others have weak IMFs. Water, as you know, has three actual intermolecular forces. It has hydrogen bonding, which is the strongest. Has London dispersion force is the weakest, and dipole-dipole, which is another version of the hydrogen bond here. But those intermolecular forces are very strong between adjacent water molecules, which I've shown as particles here. And because those IMFs are strong, it takes a lot of heat to break those IMFs and allow the water molecules to escape the gas phase. If you go to that group 6A in the periodic chart where oxygen is the first element, underneath it is sulfur. So oxygen would form water, which has a boiling point of 100 degrees Celsius. The analogous compound with sulfur, H2S, okay, would have a boiling point below 0 degrees Celsius. Okay. And that's because sulfur cannot form the hydrogen bonds that oxygen can. So the boiling point is a lot lower. There aren't these strong intermolecular forces between H2S molecules. Therefore, it's easy for them to escape into the gas phase. Basically, the only type of intermolecular force you have between H2S molecules is the London dispersion force, because the electronegativity of sulfur is so much lower than that of oxygen. Okay, oxygen electronegativity of 3.5. Sulfur is probably about 2.2 or something like that. And hydrogen is 2.1. So it's nonpolar covalent, whereas water is polar covalent. So that's another factor that affects boiling points, aside from altitude. That's not so important in our discussion of freezing point depression and boiling point elevation. Let's go back to that. So last time we talked about boiling point elevation. We said that whenever we add a solute to a solvent to make a solution, that the boiling point of the solution is higher than that of the pure solvent. I use water as an example. Okay, most of our solutions are in water. We know that water boils at 100 degrees Celsius. It's actually 100 with an infinite number of zeros after it. So if we make a solution of something in water, it's going to boil at a higher temperature, maybe 101 degrees Celsius. That change in temperature would be 1 degree Celsius there. That's our boiling point elevation. Another example here, starting out with water, boiling at 100. If we add solutes, say sodium chloride to the water, maybe it boils at 101 degrees Celsius. But it's an increase in boiling point. That boiling point elevation, which we'll call delta T, would be 1 degree Celsius here, the difference between the two. Van Hoff figured out how you can actually calculate delta T. So he said that the boiling point of the solution is equal to the boiling point of the pure solvent, which here I'm using water as an example, plus the change in boiling point due to the solids in the solvent. And his equation to calculate delta T is given here, which I would give you on a test. I won't tell you what the symbols represent. That rise, that increase in boiling point can be computed two ways: by the difference between the boiling points of the solution and the solvent, if you're given that. If you're not given that delta T, then you can calculate by multiplying these three factors together. I representing the number of ions that are formed when an ionic substance dissolves in water. Kb being a constant depending on the solvent. So Kb for water is different than Kb, say, for alcohol. And then the third factor, the molality of the solution, which takes into account the number of particles of solute in the solvent there. Number of moles of solute, and number of kilograms of solvent that you should know. So number of moles is proportional to number of particles. So the more concentrated the solution is, the more concentrated a solution is, the higher the molality, and the larger is the increase in boiling point. So as for I goes, if you have a covalent compound, you can assume it's not going to ionize. An example would be carbon compounds. They're usually not going to ionize. I is automatically equal to 1. If you have a salt, a metal, and a non-metal making an ionic compound, they will always ionize. So when they ionize through completion reactions, there aren't any of the reactants left over. They all convert to products. You count up this number of products here using the stoichiometric coefficients. 1 plus 1 gives you I is equal to 2. For calcium chloride, 1 plus 2 gives I equal to 3. That calcium chloride would have this type of a particle model. Positive calcium and 2 negative 1 chlorides. They're attracted and held together by that electrostatic force of attraction in the ionic bond. When you put that in water, that bond breaks, giving 3 particles. So you can actually count up the number of particles using stoichiometric coefficients from the ionization equation. So on an examination, we're on your quiz. If I ask you to do one of these types of problems, which I will, I'm going to ask you to write the chemical equation explaining your value for I. If you can't do that, you'll lose some points on the quiz. So ionic compounds, metal and non-metal, always have I bigger than 1. It's going to be an integer. You basically look for a metal on the left side of the chart and a non-metal on the right side of the chart. All right, so as far as units went, I explained that last time. I has no units, it's just a number, infinite number of decimal places. Kb must have these units because molality is in moles per kilogram, and we're getting degrees Celsius here. So in other words, since molality must have these units, and since delta T must have these units, to get delta C over here, Kb is forced to have these units here because we have to cancel out kilograms and moles to get degrees Celsius alone. It's the same idea for a freezing point depression, but instead of the temperature of the solution going up, the temperature goes down. Think about antifreeze in water. It makes a solution with a higher boiling point and a lower freezing point to protect the radiator in the winter. Use the same type of equation. Really, the only difference is Kf. K for freezing point also depends on the solvent. It's different than Kb for boiling point. You're there. You don't need that. Kf for water is 1.86. Kb for water is 0.52. So these boiling point elevation and freezing point depression constants are different for the same solvent. I would give that to you on a test. I would give you the units as well. So then, to compute that freezing point depression, you calculate delta T by multiplying these three things together, right? Only you have to remember that you have to subtract this delta T that you get from the freezing point of your solvent. So, because each of these factors in this equation is a positive number, you're going to get delta T as a positive number. The freezing point of the solution is then going to be equal to the freezing point of the pure solvent minus delta T. Freezing point depression means that you subtract this positive delta T from the freezing point of the solvent. So if you have water, I would expect you to know that for water, this would be the equation here. Water has a freezing point of 0. The freezing point of an aqueous solution is always going to be a negative delta T in degrees Celsius. But if you had some other solvent, maybe something that froze at 3 degrees Celsius, then it'd be 3 minus delta T. Or if you had something that froze below 0 degrees, it'd be minus number minus delta T. You got to remember to subtract this for freezing point depression and add it for boiling point elevation. I actually have it there. So, I wouldn't suggest that you memorize this algorithm. Instead, you should understand the concept and know that you need to subtract for freezing and add for boiling. I talked about why this happens. When you have an aqueous solution, you have a lot of hydrogen bonds between the water molecules. And when you add a salt like sodium chloride, those dissolved ions disrupt those bonds and cause the freezing and boiling points to change. Next one up is osmotic pressure. It's the pressure in atmospheres exerted by water across a semi-permeable membrane that divides two solutions of unequal molar concentrations. So I remember when I taught high school biology, I did this as an experiment for the students. I set it up in the morning, I let it go all day long. So basically you take a big beaker in which you put, say, pure water, okay? And then you have a tube, all right? And then you have the tube attached to some kind of a semi-permeable membrane like animal intestine, which was what I use. I bought it. It's really kind of like that, but it forms a chamber, and you fill that up with a colored salt solution. This could be a sugar solution, could be sodium chloride solution, and to make it more visible, I threw some dye in there. So you have a solution here, and you have water out here. So there are different concentrations. There's no solute out here. What happens is that these two want to come to the same concentration. And since the semi-permeable membrane only lets water to flow in or out, it won't let the solute flow in or out. The pore sizes are too small. The only way that these two solutions can come to the same concentration is that water goes in and dilutes the solution, the salt solution. It's trying to dilute the salt solution to the extent that you only have water on either side. So water goes into this solution here. If it's fairly rigid, then it can't expand very much. But what will happen is that as the water flows in, it'll force liquid up through this tube. So this tube continually increases in height during the day. And it's because there's a pressure forcing water into the tube and into the chamber and up the tube. And that's called osmotic pressure. That you don't really need to understand so much, but you do need to be able to calculate it. We can derive the equation for osmotic pressure from the ideal gas law. So remember, PV equals nRT. If we solve for pressure by dividing by volume, divide the left side by V, it cancels out, ends up on the right side. We'll put it under N. N is number of moles, right? N over V is number of moles over volume, which is number of liters. Isn't that the same as molarity? It is, which we give the uppercase symbol M for. So we'll replace N over V by M molarity. And we end up with this equation here. To make it different from the ideal gas law, we'll use the Greek symbol P for pressure, pi. So that becomes our osmotic pressure, and this is the osmotic pressure equation. Pi equals mRT. I corrects for the case where you have a solute that ionizes. I equals 1 for carbon compounds. I is bigger than 1, always an integer for a compound that gives ions in solutions. So you can compute osmotic pressure by taking the number of product ions times the molarity of the solution times the gas constant R and times the temperature. Now, as far as units go for these things here, pretty easy to figure it out. Okay. So here are the variables explained. To figure out what the units have to be for everything in this equation, you have to look at R, the gas constant R. Remember from Chem 121, it had a value of 0.08206 liters atmospheres moles per Kelvin. You don't need to memorize that. You don't need to memorize the units. I'll give it to you. But the units of R tell you the units of everything else in this equation. Right? Because R is per Kelvin here, that forces capital T here to be in Kelvin. So this must be in Kelvin. Because R is in atmospheres, that means that the pressure you're going to compute is going to be in atmospheres. All right, so then what you're left with is liters over moles. So then that tells you that M must be in moles per liter, normal units for molarity. So when you multiply I, which has no units, times moles per liter times R's units times Kelvin, the Kelvins cancel. Let's see, the moles and the liters cancel. You're left with atmospheres for pi. Okay? I think I put one of these on your first quiz, right? Probably next week. All right, so next we're going to look at some problems from this section here. This one is more conceptual. All right, so this equation here, it has the I in it. You know, from my viewpoint, you could just write this equation like this, where that's the total concentration of all ions in solution. Instead of calculating the concentration by multiplying it by I, instead you could just calculate the molality by calculating it as the number of moles of ions in solution. Okay, that's the only thing I'm saying here. So for sodium chloride, if you had 0.1 molal, that means 0.1 moles of NaCl per kilogram of solvent water. Assume this is water here. The sodium chloride, when you put it in water, is going to do this. Right, so I is equal to 2. So the total concentration, Cm total, is going to be 2 times 0.1 equals 0.2. So I'm just saying you could have actually used 0.2 for Cm instead of saying 2 times 0.1. For MgF2, when you put this in water, it's going to give Mg2 plus 2 fluorides. I is equal to 3. So Cm total would be 3 times 1, or 3 moles per kilogram. And for the last one here, methanol is a carbon compound. It doesn't ionize. I is equal to 1. So Cm total is equal to the concentration of the unionized methanol because it doesn't ionize. That's more conceptual than anything else. You'll actually be doing a freezing point depression experiment, maybe experiment number 3. All right, so next one, arrange the substances in order of decreasing freezing point. So we have sodium chloride, ammonia, magnesium chloride, and another ammonia solution. So let's just write them down. So we have one compound, sodium chloride, 0.3. Put up here molal concentration. Ammonia, let's see if we can do some kind of an order instead. We'll go from, say, low to high concentration. So ammonia, molal concentration 0.25. That's that one there. Magnesium chloride, 0.25 molal. See, sodium chloride, 0.30. And then ammonia, our second solution, 0.75. So we want to arrange these in order of, say, decreasing freezing point. So we know that the freezing point of a solution is equal to the freezing point of the solvent, pure solvent, minus the freezing point depression delta T. And we assume these are all aqueous solutions, right? So for every one of these, since water is the solvent here, we could say this is equal to 0, 0. Let's see. Well, let's look at that Van Hoff equation. That would be I, KF, CN. All right, so we can see from this, the larger the delta T, the smaller is the freezing point of the solution. The larger the magnitude of this delta T is, because we're flipping it negative there, the lower is the freezing point of the solution. So the most concentrated solution has the lowest freezing point. So we can come over here and do TF now. This is most concentrated, isn't it? 0.75. So this should have lowest freezing point here. All right. But we also have to take into account the I here. So let's do an I here. NH3 doesn't ionize. I is equal to 1. I is 1 there. Sodium chloride ionizes. You put it in water. It does this. It's a completion reaction. None of it is left. I is equal to 2. Magnesium chloride, metal, nonmetal. It's an ionic compound as well. Magnesium is group 2A, forms a cation with a positive T charge. End up with 2 chlorides out of this. When it all ionizes, none of the reactant is left. Count up the stoichiometric coefficients, I is equal to 3. Okay. So the effective concentration, when we multiply I times Cm, not using the Kf here because it's just a constant. When we multiply I times Cm, we get the total concentration of everything in solution, like I pointed out in the last problem. So 3 times 0.25 changes this to 0.75. Okay, so this should be the lowest as well. I is equal to 2 times, so 2 times 0.3 is 0.60. That's next highest. And the ammonia doesn't, so it has the highest. So we could now reorder these. It says in terms of decreasing freezing point. Well, to be honest with you, I don't really care what order you put these in. You could put them in order of increasing freezing point or decreasing freezing point. You just have to let me know which one is the high, which one is lower. You can use greater or less than signs. So the highest, I'll say highest here, highest freezing point would be the ammonia at 0.2 molal. Next lower would be the NaCl, okay, originally 0.3 molal. And then the two lowest would be the magnesium chloride, originally given as 0.25 molal, and the ammonia, 0.25, 0.75 molal. Okay. You can calculate them out, but you don't need to. Okay. The highest concentration have the lowest freezing point. These two, we said probably equal because 3 times 0.25 makes it 0.75. In reality, I think that you're going to find that this is going to be slightly larger than the NH3. It turns out that when you have a lot of magnesium and chloride ions dissolved in solution, they can form ion pairs. So some of these cations and anions would be bound up in these ion pairs. And it's going to decrease the effective number of ions in solution. You don't need to know that for a test. I've done solution chemistry research where we had to take this stuff into account. Okay. All right, so then this one here. I want you to see if you can do this one. I think this one should be fairly straightforward. An aqueous solution is 0.2 molal in sodium chloride. Compute the solution boiling point, given that the Kb, the boiling point elevation constant, is 0.512. So you can strategize on this. There's different ways to approach the problem. You could approach it by writing down all the givens, everything that you're given, assigning variables to the numbers, or you could approach it from the endpoint. What is that final boiling point that you're going to need? We'll solve it both ways. Okay. So we could start by actually translating each of the phrases in here into variables and assign numbers. So it's an aqueous solution. So we have sodium chloride solute in solvent water. It's our solute and it's our solvent. All right, so let C concentration molal for sodium chloride be 0.200. That'd be moles of sodium chloride per kilogram of water. You can just write lowercase m if you wanted. It would be okay. But this is really what it means. It might help you actually writing the molal concentration this way because it kind of tells you what the different parts of the definition mean. So that's our molal concentration of sodium chloride. Right. Compute the boiling point. So we need boiling point T sub B, temperature of boiling of the solution. We're going to compute. I wrote that next because it's the second thing in the question. It says, what is the Van Hoff factor I? Well, we've seen this one before. Sodium chloride, when you put it in water, being an ionic compound, it ionizes. None of the reactant is left over. We form two product ions, so I is equal to 2. And we're given K sub B 0.512. All right, so solution boiling point. So T, B, boiling point of the solution, is equal to boiling point of pure solvent plus the boiling point elevation, delta T. Our solvent here is water. You could have started out with this equation, but delta T, but our delta T is I, KB, CM, right? It didn't tell you in the problem, but this is an aqueous solution. That means the solvent is water, and the boiling point of water is exactly 100 degrees Celsius. You can tack on as many zeros as you like. So then the second factor here, since we had sodium chloride and we already determined I is equal to 2, the first factor is 2. Second factor is given, 0.512. And the third factor we were given as well. So we can compute that out. Two times 0.512 times 0.2, 0.205. We have 3 sig figs in these numbers here, so we could, if we wanted to be exact, this would be our answer here. However, we don't have any thermometers in our lab that allow you to read to 3 decimal places. So I've had some that read to 2. They were like 5 feet tall. You know, they actually made them. They probably have some digital stuff nowadays, but it would be okay just to write the answer as this. I would accept this because you're not going to be able to measure to 2 or 3 decimal places in the lab. So this is something I probably wouldn't hit you on for sig figs. This is the sig fig answer. This is more realistic here. See how I got that? Questions? So you got to be able to visualize this. It says an aqueous solution of sodium chloride in water. It means sodium chloride salt is dissolved in water. A salt, a saline solution. All right, so then I go to this one here. That's number 4. Given that the boiling point of a solution containing glucose in water is 101.27 Celsius, find the molality of the solution given that Kb is 0.512. So our solute is the glucose and our solvent is the water. It's a sugar water solution. So this time we're given the boiling point of the solution. That means the glucose in the water is 101.27. Right? We know that it can't be just water, because water itself, now given the problem you need to know, always has a boiling point of exactly 100 degrees Celsius. We're assuming we're at sea level. So that's our solution boiling point. It says find the molality of the solution, Cm. Okay. Given that Kb is this number here. So just seeing that Kb there and talking about boiling point, you should think that you're going to need that boiling point elevation equation. So Tb of solution, which is 101.27 degrees Celsius, is equal to boiling point of the pure solvent, which is water, plus the increase in boiling point, delta T, the boiling point elevation. So for water, okay. All right, so then we could compute delta T. And then we can use that Van 't Hoff equation. Delta T is I, Kb, Cm. There. And that will allow us to compute the solution molality. That's what we're after. Okay, so 1.27. Glucose is a carbon-based compound. I've told you that here. So I is automatically equal to 1. Kb is given 0.512. And the last factor is that. Therefore, the molal concentration is 1.27 over 0.512. You'd say 2.48 molal, lowercase m, or you could write out the word molal, or you could say moles of glucose per kilogram of solvent water. Did that make sense to you? I see a few yes, and others. Some of you look like you're zombies this morning. Get some coffee or something. 5. This was a little bit more challenging here, but I think it's a fun problem to unravel this puzzle. A solution contains 0.21 moles of water dissolved in 500 grams of phenol. Select data from the table below to find the boiling point elevation and the solution boiling point. So, for water and phenol, assuming these are solvents, they would have Kb values of 0.512 and 3.56, and these boiling points here. That would be for like pure solvent. So this would be pure solvent water, has a boiling point of 100. Pure solvent phenol has a boiling point of 182. By the way, phenol is a very poisonous compound. You could die by getting a drop of it on your hands. It dissolves into your skin very quickly. All right, so then let's read the problem. It says 0.21 moles of water dissolved in 500 grams of phenol. So in this particular case, our solute is water and our solvent is phenol. This might be tricky because in most cases it's going to be the opposite. I'm going to use water as the solvent most of the time. In this particular case, it tells you, it says water and phenol and a small amount of water and a large amount of phenol. So the solute here is the water and the solvent here is phenol. That means that we need to treat phenol as the solvent here, and we don't need the data here for the water. We're going to need this phenol data because it's our solvent here. And since we're talking about boiling point elevation, we don't need the freezing point information on that as well. So we need these two numbers, the Kb for phenol as the solvent and its boiling point. All right, so we want the boiling point elevation and the solution boiling point. So boiling point of solution is equal to boiling point of solvent, which is phenol here, plus the boiling point elevation, which is delta T. From our table, boiling point of phenol is 182.00 degrees Celsius. And our delta T then is going to be I Kb times Cm. So that's 182.00. Phenol is a carbon-based compound, so I is automatically equal to 1. The Kb here is 3.56. And our molal concentration, not given explicitly, our Cm is going to be number of moles of water in number of kilograms of phenol. It says 0.21 moles of water. And 500 grams of phenol is how many kilograms of phenol?
Half a kilogram.
Yeah, so. Okay. So 0.21 divided by 0.5, wouldn't that be equal to 0.42? And I would accept that as an answer, because you're probably not going to have a thermometer that goes to 2 decimal places. Okay? I could have had you compute freezing point as well. Yeah. All right, so this next one here is a little bit tougher because you may not remember how to actually do mass percent conversions to molality. In fact, maybe you didn't even cover it in Chem 121, so I will go over this one here because I think it's a nice problem that kind of helps you get more proficient in using concentration measurements. So it says, find the freezing point of a 12% solution of ethanol in water. So this would be like wine, so maybe a winery. Given that the Kf for water is 1.86, and that formula for ethanol is C2H5OH. So our solute here is ethanol, and our solvent is water. So we're saying this is a mass percent here. We want the freezing point of the solution, which is going to be equal to the freezing point of the solvent water, which we know is 0.00 degrees Celsius, minus the freezing point depression. Or we could say this is equal to minus I is equal to 1 because ethanol is a carbon-based compound, doesn't ionize. Kf, 1.86 times molality. So all that we need to complete the problem is find the molal concentration of ethanol in water. What we're given is that we have 12% by mass I think the easiest way to solve one of these percent mass problems is to assume, you have to take a sample amount, assume 100 grams of sample or solution. Assume that we have 100 grams of solution, okay? So if we have 100 grams of solution, and it's 12% by mass ethanol, then in 100 grams, wouldn't we have 12 grams of ethanol? You do the multiplication, 12% or 0.12 times 100 is 12. But if you have 100 grams of something, I make an analogy. If you're using percent, since percents always add up to 100, just take 100 grams as your sample amount because then the percent becomes the mass of that component. If you have 100 grams and it's 12% by mass ethanol, then 100 grams would contain 12 grams of ethanol. How much water would it have? It would have 88 grams of water. 100 minus 12 is 88 grams of water. Okay. Right. Molality, this is where knowing the definition is going to help. CM, molality, is number of moles of solute, which is ethanol, over number of kilograms of solvent, which is water. So to complete this, we need the numerator and denominator. That's why I think it's really important that you not just use molality as a number, but be able to break it down into its solute and solvent components. Well, 88 grams of water, that's pretty easy. Divide by 1,000, that's 0.088 kilograms of water. So right? Move decimal place 3 places to the left. So the number of kilograms is easily obtained from the grams by dividing by 1,000. But to get the number of moles of ethanol, we need the molar mass of ethanol. That's why we have a formula here. The molar mass of C2H5OH is going to be 2 times 12.01 for the carbon, plus 5 plus 1 plus 6 hydrogens, each with an atomic weight of 1.01, plus 1 oxygen with an atomic weight of 16. So 24.02 plus 6.06 plus 16, 46.08 grams per mole. So number of moles of ethanol, I'll use ETOH here as my symbol for ethanol, computed by taking the mass, 12 grams, over the molar mass, the algorithm way. Or you could use dimensional analysis, 12 grams over 1 times 1 mole of ethanol per 46.08 grams of ethanol. 12 divided by 46.08, 0.260. It's our number of moles. So we put that in here. You're on time. Okay. 0.26 divided by 0.088 is 2.96 moles per kilogram. We can plug that up here. Multiply out so the answer is minus 5.51 degrees Celsius. The solution is going to boil 5 degrees below zero, or freeze 5 degrees below zero, right? So it could freeze. I think it's a nice problem. I think you should be able to do that conversion. Percent mass to molality. You do it by assuming 100 grams of sample, and then the percents become the amounts of each one. Solute and solvent. If we have time, we'll go back and do the next one. Let's see, but I want to do some osmotic pressure. Since you have a quiz coming up, we're going to have to do one. Compute the osmotic pressure for a solution containing sucrose, whose formula is given, in water. You're given that molarity of sucrose. You're given a temperature, and you're given a value for R. So we go to that osmotic pressure equation, which I think you should know. Sucrose is a sugar. It's carbon-based, so it does not ionize. So I is equal to 1. M is molarity, which you're given. R is the gas constant. You're given it 0.08206 liter atmosphere, mole Kelvin. And you're given a temperature of 25 degrees Celsius. Does it look right? What's wrong? Yeah. Because our R is given in Kelvin here. Remember, temperature in Kelvin is equal to 273 plus degrees Celsius. So I did this because it's a mistake that a few students will make on an examination. All right, so we had 25 to 273. I think that's 298. So no one should really make that mistake. So then we can multiply things out. The liters cancel, the moles cancel, and the kelvins cancel. So 1 double E negative 3 times 0.08206 times 298. And I get atmospheres because pressure's atmospheres there. Okay, so then 1 atmosphere is 760 millimeters of mercury. If you didn't know that on a test, if I didn't have it on the equation sheet, you could ask me, I would give it to you. So we multiply this by 760. Oh, probably have one of these on your homework. Okay. And then the next problem here, number 9, is really the same as 8, except we're using sodium chloride as our solute instead of sucrose. So in this particular case, an aqueous solution in water, you should know that it does this, so I is equal to 2. So we have the same numbers as before, except the I is different, so everything's going to be doubled. So pi is going to be equal to 0.0488 atmospheres, or okay. And we'll stop here. Next time we'll start out with the last problem in this section, then we'll start on thermo. Email me your questions if you have any.